Okay, it's me back on the longest study day ever. Okay, not the longest, but it's up there. It's definitely up there. Midterm, midterm. That's a new term I came up with. And there's a midterm coming up on Wednesday, and I'm getting ready for it. These are all things I've done a bajillion exercises on, but I'm still a little rusty, and so I'm going to work through them with you now. Speaking of rusty, hey, that was an accidental segue, but it's pretty good. Speaking of rusty, I want to talk about standard enthalpies of formation. Now, that has nothing to do with rust by itself, but you'll see why I said rusty in just a minute. Let's say I had prepared for this and had a brush. Okay, let's say you have some iron just sitting around. Turns out that iron is oxidized, so really it's just rust. Okay, so I'm going to say Fe2 plus O3. Okay, got some of that sitting around, and let's say, oh, by the way, this is a solid. Now, let's say you've got some, oh, I don't know, let's say you've got some aluminum sitting around. And you get this crazy idea in your head. What would happen if I put them together? Now I'm going to tell you don't, because you'll probably burn yourself and it's not a good idea. But if you were to put them together, oh, you know, I gave something away. Let's back up just a little bit, okay? Pretend I didn't write that. You have some aluminum sitting around, it's solid, okay? And this aluminum, you combine it with the rust over there, and voila, you get aluminum oxide. And you also get some iron. Oops. Yeah, I gotta plan my space out better. Okay. So you get some. Oh, see, I'm doing it again. I'm writing the balanced one for my notes. I don't want to do that yet. Okay. So I want to balance because I need practice balancing. So you get some Fe. But wait, some Fe? You like that? No, some F and iron. All right. There we go. So this is my equation. This is my unbalanced equation. And if we've learned anything at all, it's that I do not plan my space well, but I'm going to do something here to fix that. This is my equation I want to start from, and I'm going to take this little guy over here, and because I'm a Photoshop whiz, much more so than chemistry. Maybe I am. Come on, you can do it. You can do it. Come on. Talking to the computer now. Okay, there we go. Let's just move that right over here. Oh, come on. My tablets have severe anxiety right now, and yeah. You hear that? Okay. Yeah, my drawing tablet, it's dying. I'm sad, because I really like it, and I use it a lot. Okay. Anyway, before I get into what I'm going to do with this, I had to go look this up. I've seen definitions in a bunch of places, but this one seemed pretty solid. So let's talk a bit about enthalpy. Okay? First thing about enthalpy is that I've been pronouncing wrong.
Enthalpy.
Enthalpy. Okay, so this is what it is. A thermodynamic quantity equivalent to the total heat content in the system. It's equal to the internal energy of the system plus the product of the pressure and the volume. There must be an easier way to say that, right? We could say that the enthalpy, let's go to B here. Okay. For this reaction, okay, you might see it like this. And assuming standard conditions, we put a little thing up here. Okay. We could say that that's going to be equal to, now they said in the definition, they said it's the total heat content of the system, so maybe we'd say it's Q, right, for heat, and that it would also include the product of the pressure and the volume, right? So the pressure times the volume, and I'm going to say change in volume, right, because if you have two states, but we're not too worried about that. Now, something you may be asked to do is take an equation like this, and they'll probably be nice and balance it for you, and then they'll have you get to what this number would be by adding together other known standard enthalpies of formation. So for example, what does it take to make an iron oxide molecule, right? Or what is it? Well, this we don't have to worry about what it takes to make that because, well, I'll show you in a minute. Okay. Yeah. Okay. So if we know pieces of this and we're only missing one, we can just kind of solve it algebraically and get to something that's more meaningful in terms of what the formation reaction for that particular substance is. And that's what I'm going to do right now. First of all, I need to balance the equation. So I'm going to write out the elements on the side here. Okay. So let's do that. I'm going to say I've got iron. I've got oxygen. I've got aluminum, right? Okay. Now if I look over on this side, I've got aluminum. Let's do it in the same order though, or else it'll be confusing. Okay. Do I have anything that's different? No, they're all the same. So this is, yeah, mostly there, but we need to just work out a few details. I don't need this equation anymore. Okay. That's probably just going to confuse things. I'm going to have an oxygen here and an aluminum over here also, and ideally they should come out to be the same, right? So how many irons do I have? I have 2 irons, right? I have 3 oxygens, and I have 1 aluminum. On this side I have 1, right? And I have 2 aluminums. That's also a problem, right? And so the oxygens, I have 3 of those. Well, at least that's stuck, but that's really not going to help us at all because we're going to have to flip some things around to make this work. So looking at both sides, what's going to be the easiest? I think I'm going to, well, do I really want to do that? Yeah, I'm going to go with the more complex ones first. So I've got 3, 2, 3, 2. Let's see if I want to. Did I say I have 3 over here? Yeah, I've got 3 over here. Okay. All right. Well, maybe I want to. Yeah, this is what happens to me in class too. Let us freeze for a minute. Okay. Well, I can see one right away. I need 2 of these right over here. So I'm going to say 2 aluminum, and that makes 2 aluminum. That's an easy win, right? All right, now I've got this. 2, 3, 2, 2, 3, 2. Oh, why am I? Jeez, that was not hard. I don't know why that was so much trouble. Okay, so let's make sure that's right. If I have 2 irons, that matches this 2 over here. 3, 3, 2, 2. Okay, we're good. That's balanced. All right, now I've got my reaction and I've got the right quantities on each side. I can start doing some work. If I wanted to, I could look up a table of standard enthalpies. Now, one thing is to form iron, or just let's not iron, excuse me, pure elemental aluminum like this. What does it take? Well, nothing. Okay, so that's the first thing we can say. That's an easy one. Okay, and we can say, what about the iron on the other side? Well, that's going to be a 0,2. It doesn't. It's already in its base, its ground state. That's probably not the right word to use for that, but it's as low energy as it's going to get, like that. Okay. So all I need to be worried about now is the formation of these guys right over here. Okay. So there are a couple things I can look at. I could say, what's the standard heat of formation for the iron oxide? Well, I'm hoping I'm going to find it right over here. So this is on Wikipedia. F. Oh boy, I thought there would be more here. Let's just do a search for iron. Okay, iron. Okay, there are a whole bunch of possibilities here, right? I'm sorry, but that just was tight. That's funny. Okay, so looking at that, which iron are we looking at? Right, it could be iron 2 or iron 3. I don't know. Well, if there are 3 oxygens, right? Let's just do a little scratch work over here. If I had 3 oxygens and they have 2 open spots each, and I would write that 2 negative, right? Then the iron, because that's going to be 6 valence electrons now I'm talking about, right? The iron, to get to that point, would have to be iron 3, right? Iron 3 times 2 is 6, yes. So that's going to be iron 2. I think that's right. No, 3. Sorry. 3 would be 3 times 2 is 6. 3 times 2 is 6. 3 times these 2 is 6, right? Does that work? I think that works. Let me think about that for a minute. Yeah, okay, let's go with that. So you can fix that if I'm wrong. Please do. I would appreciate it. So I'm looking for iron 3. Iron 3. Not chloride. Okay. Iron 3 oxide. Iron 3 oxide. Magnetite? Or hematite? Well, I didn't expect this to be so confusing. Actually, I think here's what we want right here. Iron 3 oxide. Now, I don't know the difference between these two, but you know, I've seen this perform for me before, and that's the one I'm going to go with. So I'm going to say standard heated formation for that. Okay. I'm just going to put them up here in a list so we can look at them all together. But not before I completely lose my place, because that's funny, right? Okay, iron 3 oxide hematite. That's going to be negative 826. Okay, so Fe2O3 solid. Standard heat of formation. It's going to be equal to, I'm running out of space here, negative 826 kilojoules per mole. Okay, and all of these are per mole. All right, the next thing that's happening in this reaction is there's some aluminum oxide left over, is the one I left out, so let's take a look at that. Okay, the aluminum oxide is going to have, let's look over here. Yeah, I'm having a rough day. I got my stylus in my mouth. Okay, so aluminum. Okay, aluminum oxide. Hey, that looks like a match, right? Yeah, it does. Let's see, aluminum oxide. Okay, yeah, Al2O3, that's going to be negative 1669.8. Okay. So, I can move it out here so I can look at it while I write it. Al2O3 solid, standard heat of formation. That's not an A, that's a delta, by the way. Is going to be equal to negative 1669 kilojoules per mole. You can remember that, okay? All right, so what is going to be the change in enthalpy, right? Enthalpy for the reaction. And again, that we're saying what is going to be the total heat content of the system when we're done. So when I add this and get this, what happens to the heat from here to here? Okay, so let's do it. That should be an easy one, right? Get my calculator. Well, let me write it out first. So, well, no, I don't need to. Yes, I'm indecisive. Let's do this. Okay, 82, negative 82. Oh, hey, it's leftovers up there. Go away. 82 point, wait, why did I do that? 826, can't even read my own handwriting. Okay, negative 826 kilojoules in the formation of this one, right? Okay. And I've got in the formation of the second one, 1669. That's also negative because it's emitting that heat, right? All right, so the way we want to figure this is, and I'll bring that back in a minute, we're going to look at the standard heat of formation for this substance at the end is, or excuse me, the change in heat, not standard heat, is going to be equal to the sum of all of the products. So I guess I could just say, look, there's an easier way to write this than would be in formula. I take the sum of all the products, that's these guys over here, and I subtract the reactants. Well, where are the reactants? they're over here. Okay? So this is a summation, each of these is, and we would want to keep them separate from each other before we perform that subtraction, right? Does that matter? Well, yes, it does, because if you don't distribute the -1, that can screw you up. All right, so this one will be easy because I've got -826 on the left side. I've got -1669 on the right side, and if I just subtract that, is that really the way I wanted to do it? Because I should have come out with a negative number, and yeah, this is where I figure things out as I go. So, you know what? I think I know what I want to do. Okay, I'm going to go this way. Okay, because this is what if we're negative, it means I had just formed this rust up here, and I'm starting out with a rust, and so is that right? That's potential energy in it, I think, is the way you would look at it. That's a better answer than what I was originally coming out with. And I know it's only a difference of a -1, but that's a big deal, right? So when I take these two and combine them, the change in heat in standard conditions is going to be equal to -843 kilojoules per mole of what? No, wait. You know what? That shouldn't be there. Excuse me. So that. Okay, I hope you didn't hear that. All right. Anyway. All right. Anyway, what I meant to say was this reaction with those molar quantities, those mass quantities, whatever you want to say, is going to kick off this much heat at the end of the reaction. That's all you need to know. Now, with that knowledge, you could say, how much rust is going to create how much energy, or how much aluminum would I need to create a certain reaction of a certain heat, or how much iron am I going to end up with based on this heat. And those would be pretty easy things to do. You just do a conversion. Now that I know that there are, for example, 2 irons for every 843 kilojoules, I can use that as a conversion factor, to find out how many grams of iron I'll wind up with. Or I can do that to any one of those. Each of these can be used with that heat of formation to get to a conversion factor, so you can calculate exactly how much of an element you need, or a molecule you need in a reaction, or how much you'll end up with when you're done. And that's where I'm going to stop, because I'm getting rambly. The end.